I'm honored now to mention again Mairi as, in this case, as professor of King's College from London, and to invite her to give the first lecture, the first invited lecture of the school. Thank you, Mairi.
Thank you very much for the invitation, and welcome to Greece, which is my home country as well. So now someone has to do something so that the projection works. Okay, here we are. So I'm going to take you to a guided tour to the early universe. Okay? So early universe cosmology. The first thing is actually to define what is cosmology. Cosmology is the study of the universe as a whole. Okay? We're not going to study stars, we're not going to study galaxies, we're going to study the whole universe. And our universe is very old and is very big. So what do we mean by that? The universe is very old. It's about 14 billion years old. Okay? And if you would like to make a comparison, our Earth is 4.5 billion years old. The Sun is 5 billion years. The oldest stars that we can see are 13 billion years old. And the universe is very big. So the objects which are further away from us, and we can see them, they are so away that the distance is 16 times 10 to the 22 kilometers away from us. So the light, which is the fastest possible that moves in the whole universe, takes about 30 billion years to arrive to us. So if you want to understand what does this mean, the light travels at about 300,000 kilometers per second. So in a year, the light travels about 10 trillion kilometers. And to have an idea, the distance between the Sun and the Earth is about 8 light minutes. So the universe is indeed very old, and it's very big. So let us consider that it's a nice evening in whichever is your home country, your home city. We are in Thessaloniki. Let us say that it's, well, it's a bit cloudy tonight. But let's say that's a nice evening and you walk around the water, and then you see at the sky, and you are amazed by the beauty, by the harmony of the stars, the galaxies which you see, and you start dreaming. You can start asking questions. How was created the universe? What is the universe made of? How does the universe evolve? What is the ultimate fate of the universe? To be able to address these questions, no matter whether we'll be able to give an answer or not, we have to use Einstein's theory of general relativity and data which come with the most precise kind of observations we have today, the observational tools of the 21st century. So if you see up in the sky, the center of our galaxy, which we call it the Milky Way, which is the plane of our observation, you will see that everything, all stars or galaxies or clusters, they go away from each other with a speed which is proportional to their distance. How could that be possible? This goes against the Newtonian law that says that two objects are going to attract each other with a force proportional to the product of their masses and inversely proportional to the square of their distance. So in order to understand the laws that define the evolution of the universe, we have to take Einstein's theory of general relativity. What Einstein said, that if you have some objects which are massive, they are going to distort your space-time, and they are going to build these very nice kind of landscapes of hills and of valleys. So space-time has an invisible structure which determines the way that we move, in the same way that you have the slopes that they are going to determine the movement of a skier, or the waves that they will tell you how somebody who does surf is going to move. And this kind of invisible kind of structure, we see it and we call it the force of gravity. Now, Einstein developed his theory in 1915, and then we know, as years went by, that was extremely successful. And let me tell you a few kinds of data that we have that confirm Einstein's theory of general relativity. So the GP mission of NASA in April 2004 has confirmed two of the fundamental kinds of predictions of laws of Einstein's theory of general relativity. The warping of space-time around a gravitational object, in that case for the experiment was the Earth, and the second one, to be able to calculate what is the amount of space-time that the spinning body, in that case was the Earth, it pulls along as it rotates. Now, Einstein's theory of general relativity predicts the existence of black holes. So in order to discuss about that, I have to tell you what black holes are. So you have the life of a star, which it is going to evolve in a particular way depending how massive it is. You start with a stellar nebula, and then you go all the way until the object it is going to use any source of energy it has. There is nothing else that it can have in order to be able to be live, and therefore is going to finish its life like a dead object. What is going to be depends how massive it was. So stars are in a kind of a balance between the pressure that goes outwards and the gravity, the gravitational attraction that goes inwards. So what you are going to have, you go to the various kinds of stages along the evolution of the star, okay? And it forms heavier and heavier and heavier kind of elements at its center. And at the end, there is nothing else, as I said, that it can burn. It runs out of fuel, it dies. How it's going to die depends how massive it was. So if the star originally was about 8–10 times the mass of our sun, then it finished its life like a white dwarf, as we call it. The mass of such objects is more or less the same, like the mass of our sun, one solar mass, and the radius about 1/100th the radius of the sun. By the way, our own sun, when it's going to die, is going to become a white dwarf. If it is heavier, between 10–20 solar masses, then it will end its life like a neutron star. It has almost the mass of the sun, but a radius which is very small. It's about 10–20 kilometers. A teaspoon of a neutron star weighs around 1 billion tons, just to give you an idea how compact this object is. The magnetic field is about 1 trillion times that of the Earth. The surface gravity of a neutron star is more than about 100 billion times that on the Earth. And finally, it spins up much, much, much faster than the Earth. And if it is even heavier, then there is nothing that can end the collapse of becoming what we call it a black hole. Now, black holes, we have, so to speak, we have seen them thanks to the Event Horizon Telescope, which is a big consortium of many countries of radio telescopes. They are able to detect radio waves of about 250–300 gigahertz. And just to give you an idea, the normal frequency that we can hear is between 20 hertz and 20,000 hertz. So thanks to that experiment, that's why I told you that in order to be able to understand the evolution of our universe, we need general relativity and we need the observational kind of data that we have in the 21st century. So on the 10th of April of 2019, we have, thanks to the Event Horizon Telescope, the first images of a supermassive black hole, about 6 billion solar masses, about 54 million light years away from us. And then, on the 12th of May of 2022, we have images of a supermassive black hole, which is at the center of our galaxy. So we were able, indeed, to see a black hole, and if you wish, somehow to confirm something that it was a theoretical prediction of the theory. We could say that it exists. We have made many studies about black holes, but we did not have the direct evidence, even though there were other ways to see that it's a very compact object there, basically by the bending of light. Now, Einstein, in 1916, he actually predicted the existence of gravitational waves. So let me tell you what are those. These are ripples of space-time, which are the effect of something very violent that takes place in the universe. Now, you have, for instance, as you can see here, that if you have massive objects which they accelerate, they are going to disrupt the space-time, and this kind of disruption is going to propagate away from the source. In the same way, like if you throw, let's say, a stone in the lake, you can see this kind of waves that go away. And if you are within the theory of general relativity, then this kind of waves, they travel at the speed of light. And because they do not interact really with anything else, they can give you very precise information about the origin, where they had originated, because they come almost without any interaction along their trajectory. Now, as I will say in a few minutes, we have seen gravitational waves, but was pretty long the path which led to the detection of gravitational waves, which says that's also to give you an idea that in order to make big discoveries, there is a continuation of works of people, and everyone contributes a little bit, so that at the end you can have really a very precise theory, something that you can test against data, some revolutionary ideas. So there are many people who actually have contributed, and just I give a few names here. 1893, this gentleman, Heaviside, he made the gravitational analog of Maxwell's equations, and he saw that they can produce waves that travel at a finite velocity. And this can be considered like the first scientific paper on gravitational waves. The second that I would like to mention is Poincaré in 1905. He assumed that gravitational force propagates at the speed of light, and therefore from that he was able to deduce that there is a time difference between any change of gravity that you have and the effect that you are going to detect. He called them ondes gravifiques in French, which view is nothing else than gravitational waves. 1912, Abraham, accelerated masses should emit gravitational waves. And then I would like to mention the revolutionary idea of Nordstrom, 1912-1913, who actually had this genius idea to say that mass and geometry are intimately connected. And then, of course, we have Einstein. Now, Einstein, as a matter of fact, he remained skeptical about the existence of the reality of gravitational waves along his whole life. So he was sometimes saying they are there, sometimes not, which actually is a reason for which study of gravitational waves, even theoretically speaking, had to wait until the death of Einstein. And then, almost a bit later, was the first international GR conferences, we call them today, which took place in Chapel Hill. And then the title of that conference was The Role of Gravitation in Physics. And the reality, the physical existence and the acceptance of gravitational waves came from the result, the combination of the results of this gentleman, Bondi, Pirani, Robinson, and Trautmann. As a matter of fact, a year before, and I make all that this kind of advertisement because he was in my college, in my university when he did that. So what he did is he had written a paper called On the Physical Significance of the Riemann Tensor, where he saw that gravitational waves are going to manifest themselves like fluctuating tidal forces on any mass that they are going to encounter along their path. And this was the most brilliant idea, because that is indeed what is the main kind of mechanism that we use in order to detect gravitational waves. Despite this, it took several decades, like 6-7 decades, and the work of hundreds of people in order to really make a detection, a direct detection of gravitational waves. So that was the final test and the final kind of success in Einstein's theory of general relativity, and that was found the direct detection of gravitational waves on the 14th of September of 2015, thanks to the two twin interferometers in the US. And this event is called GW 150914 because it was 2015 and the ninth month, the 14th day. So how does it work, okay? So what you do you have this laser that you can see here. I'm afraid that, actually, as a matter of fact, I have a pointer, I think. So you have this laser here that you send a light that is going to be split along the arms of your detector. The length of the arc is the same, okay? At the end, you have these mirrors, okay? It is reflected, it comes back. If there is no gravitational wave, that means that the length of the arms remain the same, otherwise stressed and squeezed, okay, the effect of the gravitational waves. Therefore, it will take exactly the same time to go back and forth, so you see no signal. But if, on the other hand, there is a distortion of space-time that is going to squeeze or to stretch one of the two arms, then the length will be different, the time to go back and forth will be different, and that is going to give you a signal. So what we found at that time was the result of the collision of two black holes of about 30 solar masses each, okay? About 1.3 billion light years away from us, okay? Now, the gravitational wave energy that was released due to that effect was about 10 times greater than the combined luminosity of every star and galaxy in our universe. Now, you will tell me how we did not feel anything, we didn't find ourselves squeezed or stretched. It's because it came from very, very far away. It was very much attenuated. And finally, the effect that they produced in the length was smaller than 1/1000 of the diameter of a proton. To me, being a theoretician, what fascinates me is the fact that we were able to make this measurement. So by now, we have a bit more than 100 kinds of events that we know from collision of these objects, okay? And that gives us a lot of information that is beyond the scope of what I will discuss today. All that is to tell you that Einstein's theory of general relativity has been confirmed. So I go back now to my questions. Okay, that was to see what is going to define the laws that they are going to govern the evolution of my universe, even though I will discuss a bit more. How was created the universe? So if I take Einstein's theory of general relativity, since I've proven to you, I move my hands to prove it to you that this theory is correct, then if I take that theory, then it will tell you that if I take these equations, which I'm not going to write down, so I'm not going to bother you with that, if I run them backwards in time, there is a moment where all matter, all energy that exists today, it is just in one spot, in one small point. That's what we call it Big Bang. That's from where everything started about 14 billion light years away. Now, we don't really understand what happened there. In mathematics and physics, we call it singularity. Forget it this moment. What it says is that they have an infinite amount in a point. So that's something which exists here. We don't understand. Our theory is not going to tell us where it comes from. And then we might also be tempted to ask, how did the universe come into being? What was there before the Big Bang? You might say there are philosophical questions, but there are questions that if you want to go backwards, at some point you hit the point zero and you say, what was before that? Is this singularity, this point where everything goes, all the mass, all the energy, it goes to a point, everything, is it real? Or there is a problem with our theory? So there are two fundamental theories in physics, quantum mechanics and general relativity. These are the two, pillars of physics, theoretical physics, if you wish. They seem to be incompatible with each other. There is a limit at which one theory works. There is another limit at which the other theory works. But there are some moments where you need both of them, to understand exactly what happened at the Big Bang, and as well to understand what happens inside black holes. So we need to build a theory that will make our friends Einstein and Planck to be happily together. Some theory that can be able to, so even though GR has been tested, this theory at some point it reaches its limitations. I'm sure many of you have seen this Big Bang theory kind of sketch that exists in the I think it exists in Greece as well, probably exists in Balkan countries. Anyway, it exists in the States, it exists in the UK, so I'm not sure, probably you know that. Anyway, there are various theories about, I wouldn't call them theories is one. There are different proposals. What is the theory that can put together general relativity and quantum mechanics? What is the theory that can complete Einstein's theory so it's able to tell us what happened at the Big Bang? And I'm going to tell you two classes of these theories. I'm not going to tell you, because just to give you their definitions. One is string theory. So it tells you that the particles are not point-like, are like strings. And you can have two types of these strings, open ones, no ends, or closed ones. Vibration of these strings give you different states at the different particles. Join a splitting of the strings, give you interactions. That's one class of theory. Sorry. There is another class of theory, which I'm going to discuss the more important, or not the more important, the more studied kind of example, which is loop quantum gravity, which tells you actually that space-time is discrete. You cannot cut it constantly to smaller and smaller pieces. At some point, you hit the fundamental structure of space-time. Now, how can you test such a theory? Can you test it? As a matter of fact, such theories need tremendous energy scales. You can never dream of making these scales in a lab. But we live in an experiment. We live within the universe where at the beginning of this, we can really have the conditions that you need quantum gravity and general relativity together. So a theory of quantum gravity, you might hear that exist proposals, should not only be consistent by itself as a mathematical theory, it should explain the nature, it should explain the universe in which we live. So early universe cosmology will somehow shed some light on which is the correct theory of quantum gravity, and then is going to describe the structure of the space-time. What came before the Big Bang? The birth of our own universe. Well, even though we cannot experience this phase, I think that it's worth trying to establish the mathematical tools, which we don't have them yet, in case some of you are in pure mathematics, in order to be able to somehow understand and unravel the mysteries of the structure of our universe. So that was how was the universe created. How does the universe evolve? So I told you that there are these equations of Einstein. The very fundamental thing is what we call it the Hubble's law, what I told you before. Everything goes away from each other with a speed which is proportional to their distance. So it's like if consider that you have a balloon, okay? And you take two stars that you put this point on the surface of the balloon, and then here. And then you blow up the balloon, and you can see now that the distance becomes bigger, okay? So you shouldn't consider that galaxies are moving through your background, through your space. No, the space is expanding, and as it expands, it drags with it the galaxies. What is going to happen then in the universe? It depends very much, the fate of the universe depends very much of the amount of material that exists in the universe, which will define what is the geometry of the universe. So we have this flat universe, and then you have open and closed. So you are not going to see this flat universe like a flat pancake. That's wrong. What you would see, if I want to find the distance between you and me, do I take Euclidean geometry, what you learned at school, or something else? Euclidean geometry tells me that the sum of the angles in a triangle is 180 degrees. If this is the correct way to find the distance, okay, so I take the square of the sum of the square roots of the three coordinates in Cartesian system, then you have a universe that is flat. It will keep expanding forever. If the sum is smaller, then you have a universe that is open. If it is bigger, then you have closed. So you have the three different kinds of geometries that depend on how much material you have, which I have not shown here. Forget this omega, but I'm not going to go into details, and will tell you what will be the fate of the universe. What is the universe made of? This is a very question. The universe is made out of stars of gas, which can be hot or cold, but mainly is made of something we don't know what it is. And what do we know that it exists since we don't know what it is? From the observational data that we have. So, as embarrassing as it is, we should admit that we don't know about 95% of the content of the universe, which we give these magic words, dark matter and dark energy. So let me tell you what the ideas are here. So you know what is very important is that it's not a mathematical theory. Mathematical theory has to be mathematically correct. But when we talk about physics, it should explain also where we live, the data we have. So how does it work? You work hand by hand between the theory and the experiment. The experiment will tell you where your kind of imagination of a theoretician breaks down. It might be correct mathematically, but does not describe the world. And then from there, you can adapt. So, normal material, like whatever all of us were made, unfortunately, is about 4% of the energy matter of the matter of the universe. Embarrassing, but true. So, let me explain that. Galaxies. The galaxies are about 60,000 light years across, and they contain about 10 billion stars. Clusters of galaxies, from hundreds to thousands of galaxies, that they are bound together with gravity. And here is the problem. If I say that what I see from where I get light, where I can go and make with my telescope and see how light it is, no matter what part of the spectrum, radio, optical, infrared, whatever you want. If I say that this object, it is as it is because of the gravity, okay, then I'm stuck. Because if I say what I see from where I see light, it can trace the matter, and I see how much matter I have, the thing should be dispersed, should not be bound. Does not have enough material for gravity to put it together. So there is a problem. So the gravity of some invisible matter must be keeping the galaxies from flying off into the space, and that we call it dark matter. Why dark? At the past, they used to call it missing matter. It's missing, dark, whatever you want. Dark because it does not have electromagnetic interaction, does not give me light. So that was already said back in 1898, 1974, during the lifetime of Zwicky. And now there are the rotation of stars, Argand galaxies, by Vera Rubin. So what you say is, if I would like to say what is the speed, I have the clusters of galaxies. What is the speed of the galaxies which are much further away from the center? It should go down as you go away from the center. There's no material otherwise to keep it going. And we see that it's flat. That means that there's an effect or more matter that we don't see within the radius of the galaxy. And what is extremely kind of issue here, that's something that's very old. We know it from a long time. We have data that confirm that, but still we have no clue what it is. If you want, we can discuss what are the possible candidates which exist, but still it's something that we don't know. And then it came even another embarrassing thing, dark energy. Our universe is expanding and expands a little faster all the time. So like what we call it, instead of decelerating, it accelerates, something that throws things further away. There is absolutely no ingredient that we know that would explain why the expansion of the universe speeds up. And that goes under the magic word, dark energy. So we have gravitational data that tell us that the universe is in accelerated expansion, but despite many efforts, despite many models, we're still inconclusive of what is the origin of this kind of evolution, this kind of dynamics that we see with the data that we have. Now, the cosmological model that we call Big Bang, which is based on Einstein's theory of general relativity, modulo, it breaks down when you go to extremely early times and to very high energy scales. It describes and explains very, very well the laws of our universe from first fraction of seconds up to now. So what it tells us, is that this Big Bang model, okay, there is a primordial soup of subatomic elements which interact with light. So once the temperature, the universe expands, the temperature drops. And once the temperature of the universe drops enough, then you have the formation of neutrons, protons, and as you can see later on, you can go and build hydrogen and helium. Now, what we do know is that, as I told you before, as the conditions allow, in the center of the stars, you have heavier and heavier kind of elements which are built. Once the stars explode and die, there is a remnant at the end, a neutron star, a black hole, a white dwarf. The new stars that they are going to be formed, they can be formed with heavier elements. So we have a very good understanding of what's going here. And what is very important, gave us a lot of data, is when you have decoupling, when you have separation between matter and between photons. And that happened about 400,000 years after the Big Bang. That at the time that you have that now photons are free to come to our telescopes, and that's when we say that at that time and onwards, the universe became transparent. Before it was opaque. And here is the big difference between electromagnetic radiation and gravitational waves. Remember what I said, they don't interact, so they can tell us, they can all the way go back to the Big Bang. So here is what happened about, as I said, 400,000 years away, okay? After the Big Bang, that at the time that the universe became transparent, okay? Hundreds of millions of years later, the universe entered what is called the reionization phase, and in the last era, which lasted about 13 billion years, we have the formation of the first galaxies and clusters of galaxies. So the universe has evolved from the initial stage, which was quasi-homogeneous gas, at this very inhomogeneous distribution of matter. You can see these filaments there, that when galaxies are formed, then you have the clusters of galaxies with voids between them. So all that is well understood. And this was extremely, as a matter of fact, you know, for many years people said, cosmology, philosophy, you say whatever you want, you cannot prove it with any data. And of course, something which is physics, you can reproduce it, you have data. So it was very important, this cosmic microwave background radiation, which is the relic of the photons of the Big Bang. Is what I told you, the photons now are free to come to us. That was found in 1965 by these guys, Perisius and Wilson, which actually they found that there is this radiation which has a black body spectrum, so it's a thermal event that gave that, which is the same from all directions. So it's not a local event. It comes always, has the same intensity all across the universe. And that gives a big evidence for the Big Bang, because that means it started from a hot thermal state. So here, so the universe expands. The temperature drops. It was very hot. It's very cold. It's about 27 degrees Kelvin. And you have these small fluctuations about this temperature, which is the black and red spots which you can see there. And these fluctuations of the average temperature is smaller than 10 to the 5, okay? 1 with 5 zeros. Extremely, 10 to the minus 5. Extremely small deviations in these small fluctuations around the 2.7 degrees Kelvin. And these deviations that we found with the instruments that we have, again, going back in the instruments of the 21st century, they agree with a universe which is flat. By flat, I mean, again, how I measure the distance between you and I. I take Euclidean Pythagorean theorem that you have only here, okay? I'm not saying that it's a pancake, a flat pancake. I'm saying that this rule that we all learned at school is applicable. That means that my universe, it's not going to collapse. It's not going from a Big Bang to a big crunch, but it's going to keep evolving forever. What is the time, the ultimate fate of the universe? Which is exactly what I said before. We're in this green curve, so the universe will keep expanding. The expansion will slow, but will keep expanding, so no worries about that. We might well, we for sure destroyed the Earth before that, but it's not going to go to a big crunch. But now this theory, which is so robust and passed all the exams, it is in agreement with Einstein's theory, has some limitations, okay? It has a big kind of success. The big success is this thermal spectrum, so everything started with a thermal initial state, a big bang, okay? It's in agreement with what we call it Big Bang nucleosynthesis, in other words, the percentage of the elements that we find, but it has some problems, okay? Actually, all good things have a problem. The universe is very flat. So the flatness of the universe, how good is to take this Pythagorean theory, okay, is something that it's something that depends on time. So the data today tell us that the universe with a very big accuracy is flat. That means it had started extremely flat at the beginning. So here is the question, why to take particular initial conditions? Okay, very simple answer could be because otherwise you and I were not going to be here. Well, but we don't like an answer like that, so we try to understand why. A second one is this kind of uniformity of the cosmic microwave background. As I told you before, or you know, of course, nothing goes faster than the speed of light. So there was no way these separated parts of the sky that have so same temperature today to have been in contact in the past, okay? So there should be some particular initial conditions. So when people don't like particular initial conditions, they try to say, well, can I find something to complement the Big Bang theory, which is based on Einstein's theory, I keep saying. So this is what they call it the inflationary model. It's not a theory. It's a model. There are thousands of studies there, but it's still a model searching for a theory. This I insist to avoid any kind of dogma that is there. So that tells us that the universe had a very, very fast expansion. So you see, if I am in the surface of a balloon, okay, and let's say that I live today in very small surface of that balloon, because my balloon exploded very much, then it is flat. Take a huge balloon, take a small area, it's flat, okay? And if everything came from a smaller region, because I had this tremendous kind of blow-up, then of course they were in contact. They were neighbors, they had the same information. So that theory tells us that the universe between 0.3601 and 0.3301 after the Big Bang, okay, it had a huge expansion of 10 to the 26 orders of magnitude. That's a theoretical model. There has been no proof. They can be under question, but that's something. So just to see that there is this back and forth between the models that we have, between the theoretical description that we invent and the data that will come to complement, to somehow put into test the proposal that we've made. So let me go back to that. There is a very important interplay between general relativity, astrophysics, particle physics, with the use of very precise measurements and observations that help us to understand our universe, its laws, and its evolution. So indeed, we live in a golden era for cosmology. You have the SKA, the Planck, the LIGO stuff there, the third generation detectors, the LISA up in the space, the LHC. So we have all these fantastic experiments that they help us to test our theories and to be as back as we can trace the history of the cosmos in which we live. Nevertheless, despite the fact that we live in a golden era of cosmology, open questions remain, and they need young people to come and reinforce us. We need to make further progress to understand the origin of the early and late acceleration of the universe, to understand what holds galaxies and clusters together. It's not only the matter we can see, as I told you before. We need a theory that can somehow cure the pathologies of Einstein's theory when we go to tremendously high energy scales. We try to understand the origin of the universe when we try to understand the interior of black holes. Even though we most probably will be, all of us, unable to experience the phase that gave birth to our universe, I think it's worth to trying to construct the mathematical tools, which I believe we don't have them yet, in order to describe these very early stages and understand the space-time of our universe. And allow me to say that this is indeed the beauty of theoretical physics. Thank you very much.
It was a fantastic trip through the history of the universe, starting from the Big Bang theory. Now it's time, if you want to put some questions, please do it.
Yep. How long the radiation what? What you are talking for the what did?
Yeah, I meant the. Thank you very much. When talking about gravitational waves, you mentioned gravitational radiation. What? And also, you mentioned that space expands at the speed at which space expands is relative to the distance.
No, what I said any two objects, they go away from each other with a speed which is proportional to their distance. Okay? So that's exactly, if you take this balloon that I draw there and you take this two spots, the way that this distance grows is going to determine the speed at which they go away. So they go, the biggest is the distance between them, the faster will be the speed away from each other.
Okay, thank you.
Okay? And the relation between the two is something that gives us the ratio at which the universe expands.
So we still have time for one question, no more. Please, please.
So can I tell you something more? For instance, I have this balloon, and I have a given ratio, and then I expand it to different ratios. The ratio of this radii, as a matter of fact, is not a straight balloon, but it's just not the idea. The ratio of these two radii gives the rate of expansion of the universe. Okay? Which is the constant of proportionality that comes between the speed of separation and their distance. And that was actually the... I didn't understand the question. How
quantum mechanics theory works? Because I got
what I said here is very important. At this particular stage, when we have this very high energy, okay, the very early universe, the position and the properties of atoms and subatomic atoms have probably this kind of machine, my science will generate that. So you have two units where one theory works and the other works. Then you get, so the universe at large, you are not going to see this. But if you go to a very small size, very caliente, then you can take this point. In the future,
Please.
there are forces.
Στο μικρόφωνο.
That's good to us, but none of them is
Okay, thank you. Let's thanks again to Mairi for this wonderful lecture. Thank you, Mairi.